couple of minutes for people to join, and then we go for this. Whew. Good Monday morning. Hi, everyone. Welcome to the 1st of December 2025. This is amazing. It's so scary how quick time goes when you're learning stuff, right? When you're learning stuff, how quick time goes. Yeah, so I'm gonna do. I used to 3 months ago, three or so months ago, I used to do 2 streams a day or something. And I would do one stream in the morning, and I would do one stream in the afternoon. I would do a software stream in the morning, and I would do a FPGA stream in the afternoon. And then I kind of got busy at a point, and I started doing only one stream a day. And then I got so busy that I couldn't do. I didn't get that busy. I just, distractions came up and things happened, and I didn't stream as much as I wanted. So the plan for this December is going to be that I'm going to try and learn how to build a digital camera on an FPGA. And my FPGA of choice is the Upduino, by Tiny Vision Upduino. The Upduino by Tiny Vision, which is based on what is this? It's based on a Lattice Ice40 Ultra UP40 Lattice, Lattice Ice40 UP5K Ultra package, Ultra something 5K means the number of lookup tables basically. So we're gonna use this FPGA, and we're gonna try and use this FPGA to build a digital camera, or some sort of thing, some sort of device that sort of works like a digital camera. Basically, we want to take signals from some. I think the thing that I promised to do was I'm going to use what is it? An OmniVision OV7670. This camera, we're gonna use this sort of camera. It's an Arduino. You can call it whatever sensor camera. It's an image sensor, and we're going to use this, and we're going to source signals from this, and I'm going to display them on some sort of I2C display or QVGA 240 by 320 display basically. So basically what we wanna do is move image data from a camera sensor like this one through in an FPGA like this one into display like this one. That's basically what we want to do this December, and that's going to be my attempt at doing Adent of Code. That's going to be my project for my own personal Adent of Code project for development. Let me let people know that this is online. Yeah, let me let people know that this is online so that we can keep going. Sorry. Sorry for being on mute so long. So the thing that we're going to try and do, as I've explained, is going to try and move an image from an image sensor through an FPGA into into some sort of display sensor, display screen. Ideally, we don't have to use an SPI display screen. We could end up using an I2C display screen. That would be really awesome, because then we would be able to save the amount of pins on this thing, because I think we only have we have a very limited amount of pins. That is 39 GPIO. So and some of those are going into power, some of those are going to be power and ground, and we need more pin. We need some pins for the display, and we need some pins for we need something like 20 pins for the camera, and then we need another thing like 7 or 6 pins for the display. And it also depends if we end up doing something like touch, which will mean we'll need more pins. But for now, that is going to be something that comes down the line. At the moment, the first thing that I would like to do it will be to just set up the project, get it started, and then also set up the I2C. This FPGA has something called hardened I2C. So a lattice I240, lattice ultra plus I240 5K. Let's just go back to the documentation of this and look at it. I won't do that much about documentation. We're going to go to the code just now, but I want to show what it can do first of all. So the features of this, it has the features, I think it's the ultra. If we look at it, if we can open it, the features of this it has hardened SPI and I2C blocks to interface with the variety of sensors and peripherals. When you see hardened SPI and when you see some hardened blocks, it means that they come baked in. They come baked in into in the silicon of the actual fabric of the FPGA. I forget all of these names because I've been working so much on doing like software that the terms escape me, but they'll come back as the month goes by. So what I wanted to do today was actually just set up some project, run a demo, and then after we run the demo, just try and attempt to set up the I2C block and see if we can get it going. And I do have some documentation that's going to help us with this. I believe I do have some documentation. So let's go look at the documents, lattice I240, and I think I have the Ultra family datasheet, but I want the hardened I2C advanced guide. So there's a guide that will help me use SPI I2C and SPI hardened. I could just search it somewhere here. Isn't there a search? There should be a search. So let's look at this user guide. Which one is this? This is just the user guide. What I want is the advanced one. The reason for wanting the advanced one is because this one is just for it depends on using the, let's look at the downloads. Let's actually go to documents, put it in I240, save it. Let's actually look at that one. So this one depends on us using, if I'm not wrong, we need to use with module generation. Yeah, so I do not want to use module generation. Use the module generator is recommended flow for the usage. Okay, cool. I do not want to use a module generator because I do not want to use lattice Radiant. I want to use the open source tools. When I2C hard IP is enabled, the necessary signals are included in the generated module. That is it. This is fine. But I want the advanced guide. The reason I want the advanced guide is because I want to use something called Appio, which is open source FPGA. Open source FPGA software for designing and programming FPGA boards. So I want to use something that is open source. So I want to actually work on the code myself rather than generate the modules. So I want to find advanced I240, I2C, and SPI hardened user guide. This is the one I want. Let's save this. This is the one I want. So this will enable us to actually do it by ourselves because it describes which registers that we want to use. So hardened I2C equal to this. It gives us the hardened I2C thing, and then we can sort of decide which registers we want to use, and we can set it up as we deem fit and as we wish. So that's what I want to do. In the meanwhile, before we get to this, let's set up a Blinky. Let's set up a Blinky and run it on the thing itself using Appio. I'll have to deal with that later because unread. Sorry, I need to close my email because this is distracting. So cool. So let's actually go and set it up using Appio and getting started. I think something like that. I think actually Appio commands, and I want to start with create. So let's create a board and a top module project for ourselves. So let's go here. I should have done something. Oh no. This is insane. So I want to close that, quit that. Yes. Sorry. Ghosty. So those are my notes, and I would not like to show them. So I want to go into documents, ls. I think cdeng, and then I will want to do rtl cam. No? So let's make a directory. Make dir rtl digicam. Yeah. cd rtl digicam. So here. So in here, what we want to do is actually initialize an Appio project. You can install Appio as a image. There's already instructions on how to install Appio and such. I'll assume that you can get this installed and such. So I want to do Appio create, and then I want to do go board, and then in here I want to supply that it is the Upduino 3, and then I want to set that my top module, isn't it? That top module is going to be main. So let's do that. It's gonna set it up. Okay. What is that? So that's cool. Cut Appio in Appio INI. Cut. Anyways, let's open this envelope. In here you can see it's set up as this is the board module, this is the main, and now we can start making files. Yeah. Okay, we can start making files. So the first thing I'm going to make in here is going to be a main.v. And in order to just get this main.v going, in order to get this main.v going, I'm going to start with the example from the Upduino the Upduino documentation repository. I'm going to start with an example from here, and in this example I'm going to take blink LED, and I'm going to take RGB blink.v. This is what we're going to do, and then I'm going to copy everything in here, and then I'm going to come and post it in here, isn't it? And then I'm going to say yes, and then I'm going to say this is using LED, blue, LED, green, LED stuff. So the next thing I need to do is actually make a PCF file. And if I recall correctly, I've done this before, so I've done this before, and I apologize if I'm moving too fast, but I think some people like it when I move fast like that. So I'm gonna look here, and I'm gonna see how I defined okay, so there's these, so I want to copy these. I just want to reference those main.pcf. So PCF is a pin control PCF is the pin control. I can remove this, I can remove this, I can remove that. PCF is the pin control file, and what we do here is we just set these pins as outputs and inputs. Basically, we set them as outputs and inputs, and this enables us to use, it's almost like your GPIO setup. On a microcontroller, it's almost like your GPIO setup on a microcontroller. So that enables us to get everything going in there. And I think the next thing we need to do is up your verify or up your lint. I did actually do a command, yeah, up your lint. Up your lint should verify that we actually have the correct code. So all of this is missing. That's fine. Those are okay. Those can be missing because those need to be they either need to be ignored or they either need to be added in a custom way, because I remember I fixed this at some point. So this is going to be months ago. And if I looked at this and at some point I would have, yeah, prevent Upbuild from raising lint errors. So that was that. So very later, mint, yeah, so there's that. So if we do that and we come back to here, or was it around SBI2C? I think, and the next one is very lent pin on, pin missing on. So that should be here. So this is just turning off the linter and on in here, and this should enable us to do everything. Something's wrong. Something is wrong. Let me see. Okay, cool. So this is the one for very late. Is that. Top module main was not found. That's fine. That's okay. So top module. So this is the top module here, over here. So top module. Let's label it main. And then if we do that and we do up your lint, it should be successful because there should be nothing wrong now. So, and what up your lint does is actually what up your lint does. Where is that? What up your lint does is just it goes through the up your lint command, checks the project source file for errors, inconsistencies, and style violations using the very later tool included with API. So now we can do a build actually, and this should actually let us build the code. And this should be good. So perfect. What build does is it synthesizes the code into something that our FPGA runs. So it takes the PCF file and it links the signals in the PCF file with the actual code that is in our the actual Verilog code that is in our main module, and then it links those two together. It just shapes them. It arranges the fabric, the FPGA fabric, so that the circuit that we have built actually works. And I think the next thing I need to do is plug this in. It's going to run the last program, which is the FPGA. We have a CPU there. We have I think a RISC-V CPU there that is actually running through instructions, and every time it runs through instructions, it changes the RGB color on the LED. So it goes on. It changes color. It'll go green. It'll start going green. Start going red. It'll start changing at some point. But what we want to do is change and run the Blinky today. That's all we want to do. Change and run the Blinky today. So let's do that. And I remember I actually have a PR that explains how to do this. So there's iceprog build default hardware bin. iceprog build default hardware bin. So this, oh yeah, there's a udev rule that I need to add. ls udev udev rules locations. Well, I can try up your flash or something also, up your format, up your upgrade, up your upload maybe. Let's see if up your upload works on this one. No matching device, ls USB, ls USB. If I recall correctly, yeah, here it is, 04036041. But it is here, 04036041, and it's this it goes to a FTDI instead of the thing. So if I recall correctly, I have a solution for this on my laptop, and if you give me 5 minutes, I should be able to get this copied over. I should be able to get this copied over. Yeah, the first streams are always quite rough, especially when you're working on something you haven't worked on in a few months. But we'll get this worked out, and it will work, and we'll keep going, and that will be awesome. I do want to, so where do, it's going to go off. That's going to be disappointing. So just trying to find the udev rules that are relevant here, and we should be able to get this right. I should have fixed this before the stream. I should have, but I didn't. And life is short. This is fine. Yeah, so ls etc udev. So rules. Okay, so which ones? So this is the ones I want. This is the ones I want. Let me make 99 Upduino rules. 99 Upduino rules. Sudo. And can I go that? Can I go here? Can I do ending? Will it allow me? Will it allow me? No. And then in here I want to make 99 Upduino rules. 99 Upduino the rules. Actually, this is quite okay, because if I didn't do it like this, then it would look magic. If you're doing this by yourself, whatever year it is that you're watching this video and you're doing this by yourself, and it doesn't work, it's going to feel like I was lying, and I wouldn't want that. And then tap. So ID vendor. It's funny that we're in here again, and we're doing USB stuff again. 0403, and then after that we're going to do ID product, and then equals to 6014. And then what are we gonna do here? Mode is equals 0660. Okay, and then group is equals plug dev, and that should be it. I kind of thought this would be an issue, so I'm gonna copy that. Copy. It's fine. Sudo. Um, 99. That should be Arduino. Dot rules. Okay, cool. So now we're here, and if we try and flash this thing, yeah, LS USB. I do see it, 6014 over here. So refresh dev rules. Is that really what I need? Is that really what I need? Yeah, please don't make me reboot. Okay, cool, whatever. So, cd documents, eng RTL digicom, ls, there's a build folder in here. Okay, cool. So, and then this one is going to be the nvim one. This is what we're working on, and then in here we're going to do ice, control R, ice prog. Can't find ICE FTDI device vendor ID 0x403 ls etc udev rules. Rules is the 99 Upduino rules. 99-Upduino.rules. Okay. Cut etc udev rules 99. Must be something I'm doing wrong here. ATTR's ID vendor equals 0403, comma ATTR's ID product it's 06014, mode 0666, group plug dev. That really should be it. ls I2C cut udev rules. Yeah, so it's in there. It is in there. Do I really need to reboot? Do I really need to reboot? I don't want to reboot. I do not want to reboot. I don't want to reboot because that's going to stop my stream, and I don't want to stop my stream because it's already halfway through my stream. This is really frustrating. This is really frustrating. So that I can do that. Copy. Sudo. Okay, cool. So that one works. And then I need to do this one, and then subsystem is equals to net. Subsystem is equals to Upduino. 99 Upduino. I did reload rules. Okay, so that seems to have worked. Now let's try iSprog. I hope this does not become there you go. I think it's blinking. Yeah, it's blinking. So what did we successfully just do right now? We just successfully built a Blinky program for the FPGA, and we loaded it on the FPGA, and it's now working on the FPGA. So now we can start working towards our actual goal, which is to actually put some sort of I2C implementation on the FPGA. And I would like to do this, I would really like it if I could do this using the open source tools. Basically, I want to do this using Appio rather than, I would like to do this using Appio rather than using Lattice Radiant, because Lattice Radiant is quite an involving thing, and I do not want to install it at the moment. And I would actually like the experience of learning how to do this using writing Verilog rather than getting some tool to generate the Verilog for me, so that way when time comes, because the reason I'm doing this is because I really need to debug a bunch of the Verilog that we use at work. And in order to debug Verilog that we use at work, I have to be quite comfortable with Verilog itself. not quite comfortable with the generation of Verilog. You can use generation and move really quickly, much quicker than I am moving right now, but then this wouldn't give you the advantage of whatever. So actually, let's actually we'll write a readme at the end. So here's our code. And the good thing about the code that I use is it actually does use some other, how do I explain this? Another SB underscore means silicon blue, which is a hardened sort of IP at some point. So let's go to the documentation of this and start looking at the documentation of the I2C block and see how we can use that. Does anyone have any questions currently? Anyone have any questions? We are kind of halfway through. Anyone have any questions? No questions. Okay, cool. So that's going. Let's start actually looking at the documentation of this. Now the hard part begins. The actual hard part. The actual hard part begins. So documents, and then we want to go lattice ICE14, and then in here we want to use the hardened IP user guide. How many pages? 48 pages. That's nothing, considering quite a bit of it is images and such. So disclaimer, we don't care about the disclaimer. Acronyms in this document, we don't really care about them. We do want to go through the introduction and such, and then we want to look at this, the I2C. I won't be, the SBI ones are down here. We won't look at them this time. We just want to look at the I2C ones and how to use them, because there's cause on the thing that actually do them. Yeah, so let's start. This is a problem. I never have a guess. Do I want to do that? So as a recap, the project that I'm trying to build is sort of like a little digicam using Verilog, and this has already been done by one of my sort of mentors and teachers at at work. This has already been done. This is not a new project. This is something that has already been done. So the work that has been done already lives on here. So if we go here, if we go here, Vision FPGA, this is a high level description. An image captured by sending a character on UART. When this dev kit is connected, the captured image is sent back over the UART at the default baud rate of that, and note that this can be changed by setting the thing. So there's already code that does such of the kind of thing that I'm going to be doing. The only difference is that the code that exists does it in a different way that we want to do it, and it's already quite a big code base. It exists, so starting to work through it would be quite difficult without kind of being able to understand what exists. So my first option is to try and build through what we have and see if we can get that going, and then once we start understanding how it goes through and how it works, then we can start working with such a thing. And the actual reason I came in here is to see if he was using SBI2C. So there is an I2C here. I do not know if he's actually using, this is a clock divider, HSOC, yeah, cool. Is he using the SBI2C? That's what I want to see. I'm looking for a hint of how to start, basically, is what I'm saying. And let's see I2C. I2C. So this sets a clock, an initializer downs, SCL in, SDA out, SDA in, and reset and that. So there's not really much to show us the way it's doing it. And I wonder if this is using that. But anyways, let's jump into the documentation and see what we can do. And see what we can discover. That slowly things are going to start making sense because we have a place to check, and we have something that works that we can check on, and we have also something that we can use on this other side. So this is going to start making sense quite slowly as we go through, as always with these things. Acronyms: FIFO, fast in, fast out, FPGA, field programmable, gate array, SPI, serial peripheral and interface. That's it. This referent guides provides guidance for the advanced usage of the I2C, LM, Ultralight and Ultra Plus, I2C and SPI IP. It is used to supplement the ISP. Note that on the module the module generator user interface flow is the recommended flow for initializing the hard IP blocks, as in that document. This document includes the following: system bus protocol, I2C register mapping, I2C SBI timing diagram, command sequences and examples. Perfect. So there might be even an example in here that we can actually use. Cool. The system bus interface for the I2C for the I240 between the FPGA user logic and the Adent IP functional box. The user can implement a system bus master interface to interact with the Adent IP system bus slave interface. The block diagram shows the supported system bus signals between the FPGA core and the Adent IP. This provides, what does this provide? This provides a detailed definition of the supported packages. So there's the clock from, this is system bus master, user logic, okay, and the system bus slave, and then IP register map. So from our logic, in order to talk to the registers that control the I2C itself, we have to speak to the system bus slave interface. We can't speak to those IP registers directly, is what this diagram is telling us. So at some point we will need to learn how to do the system bus configuration, and it's going to be difficult. So let's look at it. System bus slave interface, interface signals of the Adent IP module, SB clock I, SB TBI, SB clock I, positive edge of the clock used by the system bus interface. Okay, SB TBI, active high strobe input signal indicating the system bus slave is the target for the current transaction. Okay, cool. SB level sensitive write read control signal. Okay. Indicates a read operation, and a low indicates a read operation, and a high indicates a write operation. Okay, cool. ADRI, 8-bit wide address used to select a specific register from the register map of the IP. Now it's getting clearer. So this is how we write to some register. SBDATI, 8-bit data path used to write a byte of data to a specific register in the IP. Okay, so this one selects it, this one selects the path. Okay, SP.O, 8-bit output data path used to read a byte of data from a specific register. Okay, I see. So these are pipes. We're dealing with sort of like pipes. And this is going to be the difference between RTL and software. Because in software you make the data and then you hold it, and then you make a container on the other side, and then you pour it to that container. And what we have here is sort of a pipe that goes somewhere and a pipe that comes from somewhere. And the moment we start pouring data into this pipe, it goes to the destination, because we select the destination with the ADRI, and then the moment we start reading from a pipe, the data comes in as it is available, basically. You see, SBAC O, active high transfer acknowledged signal asserted by the IP, indicating that the requested transfer is acknowledged. Okay, cool. So note, ADRI must be set to 001 for upper left I2C and 0011 for upper right I2C2. For values SBDRI 30 table, let's look at that. So those are actually, it looks like, whoa, nice. So those are the things we need to control. Because if you've written an I2C peripheral driver for peripheral driver for a microcontroller, then these are the kinds of registers that you're going to deal with. These are the kinds of so we'll look at the definitions of them at some point, but yeah, these are the kinds of registers we're going to deal with. So this is fine. This is okay. And that's how things are done. Okay, so where's the note? Where were we? Higher than this? Oh wow, yeah. So cool. To interface with the IP, you must create a system bus master controller and the user logic. In a multiple master configuration, the system bus master outputs are multiplexed through a user defined arbiter. And if two masters request a bus in the same cycle, only the outputs of the arbitration winner reach the slave interface. Okay, so the first thing we need to do is create a system bus master controller in the user logic. Look here. So here, with the thing we're doing here when we're using this internal oscillator, we are choosing the SBHFOC as this is a silicon blue high frequency oscillator that's on the chip, and we want to use it. And we're saying we're labeling it as the user silicon blue high frequency oscillator, and then we're giving it some parameters. So the next thing we need to do in order to use the I2C block, the first thing we need to do clearly from the documentation is that we need to create a bus master. We need to create some sort of bus master. There's probably some of you who are watching this who are very competent with FPGAs, and they're like, oh, this guy is going around the wrong way. And you're very welcome to leave in a comment and tell me what I'm doing wrong. So the first thing we need to do is make a system bus master controller in the user logic. Okay, cool. So let's actually see. I'm going to take a sip of water. System bus write cycle shows the waveform of a write cycle from the perspective of the system bus slave interface. During a single write, only one byte of data is written to the IP block from the system bus master. Write operation requires a minimum of 3 clock cycles. On clock age 0, the master updates the address data and asserts control signals. During this cycle, the master updates the address on SBDRI, updates the data that will be written to IP block SP data lines, asserts the write enable SBRW signal indicating a write cycle, asserts the SBSTBI selecting a specific slave model, SBSTBI. Active high strobe input signal indicating the system bus slave is the target for the current transaction of the thing. The IP asserts on acknowledgement in response to the assertion of the strobe. Okay, cool. And then on clock age 1, so we need 3 clock edges. So an up, a down, and probably an up. If we wanna draw this, if we if we want to draw this. So Excalibur. So in order for us to send messages to the actually this is the same thing we're just gonna draw that right now. So in order to send the messages out, we have like this clock cycles. So this is clock edge 0, clock edge 1, and clock edge 2. So on one we're going to do these things. On clock edge 0 we're going to do these things. On clock edge 1 we're going to do these things, and on clock edge 2 we're going to do these things. On clock edge 1, the system bus slave decodes the input. Okay, the input signals presented by the master. During this cycle, the slave decodes the address presented by SBI2C. The slave prepares to latch the data presented in data lines. If the master waits for an active high level on the SBI2C, which is the active high transfer acknowledge signal asserted by the IP, indicating the requested transfer is acknowledged. Okay, cool. So we're waiting for that one, and then the IP may insert a wait state before the back 0, thereby allowing it to throttle the cycle speed. Any number of wait states may be added. The slave asserts back 0 signal. Okay, cool. That's fine. The following occurs on edge 2. The slave latches the data presented on the SBI lines. The master deasserts the strobe signal. So if it deasserts active high input signal increase, the IP. So the slave latches data presented on that. So we put that data when updates the data that will be returned to that. Okay, cool. The slave takes that data. Cool. It latches that data. The master deasserts the basically and enables this the write signal. SBI and write enable signal. So deasserts them. Level sensitive. Read level sensitive. Low indicates a read operation and high indicates a write operation. So now the master makes this low and makes this one low as well. The slave deasserts the acknowledge signal, which is SBI2C0. Not SBI2C0. Okay. So active high transfer knowledge signal asserted by the IP. So the slave takes the data, the master deasserts the SBI strobe signal and the write signal. So the slave takes the data. The master goes like, okay, I'm not sending any more data and I'm not writing any more data. So I'm stopping now. This is what we're doing. Okay. The slave deasserts the acknowledge signal, SBI2C0, in response to the master deassertion of the strobe signal. Cool. So this is what happens. SB clock I edge 0 edge. This is what I wrote here. This is literally what I did here. My bad. So cool. So SBI on that we send the valid address and valid data, and then SBI2C0. This is here. This is gone. So these are these actions that we've read here. Okay. System bus read cycle. So this is when we're reading from this from the system bus, and we need to read from the system bus because we might need to if we need to send data over an I2C, we then need to write to the system bus, and if we need to read data from an I2C, we need to read from the system bus itself. Okay, cool. So let's think this through. On clock edge 0, the master updates the address, data, assert controls, address, data, and assert control signals. Master updates the address line, deasserts the SB write signal indicating a read signal. Okay, cool. And then asserts the SBI selecting a specific slave module. Okay, cool. So because ADRI is going to refer to the 8-bit wide address using to select a specific register from the register map of the IP. Okay, cool. asserts the SBST strobe signal. So let's look at the strobe signal again. Active high input signal, indicating the system bus slave is the target for the current transaction. The IP asserts an acknowledgement in response to the assertion of the strobe. So what does this do? What is this doing here? Asserts this, so it says the slave is a target of this read operation. And oh, SBI2C is the one, here SB address I70 must be set to 001 for, okay, you're choosing either that I2C or this I2C. I see. So the master, once the master does 7 all the way to 0, so 7 to 4 must be for the actual I2C, which I2C you're communicating with, and then 3 to 0 is going to be which actual address in the I2C you're going to be communicating in. So where are you reading from and where are you writing to, basically? Oh my word. I have a feeling the code for this is going to be like 5 or 10 lines. That's what I have a feeling. That's what I have a feeling. That's what I have a feeling about, that this is going to be 5 or 10 lines. Okay, cool. So we know what, where is this? Read. Yeah. So asserts is that. On clock edge 1, the system bus decodes the input signals. The system bus decodes the input signals presented by the master. The following occurs. The slave decodes the address presented by the address 7 to 0. The master prepares to latch the data presented by SBI2C data lines from the system slave bus. The master waits for an active high level on the SBI2C line and prepares to terminate the cycle on the next clock edge if an active high level is detected on the back 0 acknowledge line. The IP may insert wait states before the ARC0, thereby allowing it to throttle the cycle speed. Any number of wait states may be added. The slave presents a valid data on the SBI2C data lines. The slave acknowledges that asserts back ARC0 signal in response to the strobe STBI signal. Strobe signal, whatever. STBI, let's just read that again. STBI, it doesn't tell us. High strobe input signal. Strobe input signal. Okay, cool. And then on the clock edge 2, the master latches the data presented by SBI2C. The master deasserts the strobe signal. When it deasserts, what does that mean? When it deasserts, active high input signal indicating the slave bus is a target, and then if it's low, then it indicates that it's not the target. So when you deassert it, it means the slave is not the target, which means then the master is the target. The slave deasserts the acknowledged signal in response to the master deassertion of the signal. Okay, cool. So the slave asserts this acknowledged signal. Active high transfer acknowledged signal asserted by the IP indicating the requested transfer is acknowledged. So the slave asserts this. Okay, cool. So the slave will say, I have sent you data, and then it will wait for the master to go, you are no longer the target of my current operation. And when the master goes like, you're no longer the current target of my operation, the slave goes, okay, I'm done sending the data, and it is done. And that is all presented in this wiring, in this clock diagram. So this is edge 0, this is a clock, and then this is what the strobe assert is on, and it stays on until it's off. And the CSI is not described here, so that we'll learn about that later. Read WI is read write control. So the master, this is from the master. What the slave will see is that this is pulled high, and when this is pulled high, SWI, write read. Low indicates a read operation and higher indicates a write operation. So what is this from a perspective of? No, okay, cool. So this is perfect. SBI, here you go. Here you go. It's low all the way. And then it's going to send a valid address, which I2C and which I2C and which I2C and which IP, which address in the I2C. SP data, this is just gonna stay as it is. It's gonna be up or low, whatever the data is coming to. And then data out is going to be some valid data here that is going to be on edge. So this is edge 0, edge 1. Before edge 2, this is where the valid data is sent. Wait, so we're not using double data rate. We're using one edge, so we're choosing if it's a rising edge or if it's a falling edge, and that's the one we're using. And then the acknowledge is going to be asserted, and the asserted as we've been described. So now let's look at this. Remember, they say before we even talk to the I2C, we need to make a system bus master to speak to the system bus slave. This is user logic, as you can see here. This is user logic, system bus master user logic, and then this is a system bus slave interface, and then this is the IPs that we want to talk to. So the system bus in the I240 ultralight, in the I240 ultralight provides connectivity between the FPGA user. No. This is the UL. This. Yeah. ICE LM, I240 Ultra, Ultra Plus. Okay, cool. So. We don't need this. We do not need to read this. We don't need chapter 3 because we're not using the ultralight. We're actually using the I240 Ultra. Let's confirm that. So let us confirm that by looking at the Upduino. I guess we can go read the docs or something. Read the docs. Read. Yeah, so this is the one, and I think if I can confirm that it is Upduino, it is I240 Ultra Plus. Cool. So this is Ultra Plus, I240 Ultra Plus. So we're not looking at the ultralight. We're done with the ultralight. So we'll leave that alone, and we'll come all the way to, we're going to go all the way to Adent I2C cores. These are the I2C registers. So I2C CR1, CMRDR. I remember these ones from actual things I've done before. I remember this one's from building this is cool. This makes the document half as long because we know ultralight sections can be ignored. Cool. Square, where's this node? I see. So I would like descriptions of these, but I know that CR1 is a clock control or something. As command is got that, and then this is going to be the prescaler, clock prescale register, prescale register, BR, and then CSR. I don't remember, status register, IC2X. So this is the transmit data, this is the receive data, this is the general call information, and then the slave address MSB, slave address MSB. Okay, and then this is IRQ enable and IRQ status. I remember this from, I've actually worked on I2C drivers, so I have worked on I2C drivers here. I'll show you. I will show you. So somewhere GitHub. So this is all quite familiar with me because I've worked on I2C drivers before. And there is a sample here, so either of them. In here there should be drivers, there should be source, and then it should be I2C. Yeah. And basically I understand because I've done this, it sort of is a little similar to what we're doing now. So but I2C has a specification basically. I'm running out of time. I only promised to do this until 11:15 because I have to do other work. But we've done quite a good introduction because now we know what we need to do. So I'm going to label this stream a part 1, and then we're going to have a part 2 later, basically. And I'm going to try and make sure that on the part 2 we do quite a bit more than we've done here. It's going to get faster. It's going to get faster. It's going to get faster. It's just today a lot of it was spent in making things work and such. Yeah. So there is what do we call it? There is I would like to see if there's a silicon blue. Is there a silicon blue technology library? What is this? I would like to see if there's a silicon blue what is this? Yeah, I see this SBA DFFs and SP this and SP that and I2C and ultra light, ultra plus, SFOC, LFOC, RGB. This is perfect. This is actually what we need. This is actually what we need. So remember, I am using SF. Okay, cool. That's actually plus enough. It's here. So remember, we're using this SPSFOC HFOC. This is the one we're using right now in this code, SPSFOC. So it's let's see it. The SBSF HFOC primitive generates 48 megahertz nominal clock frequency within 10 plus minus 10 variation with user programmable divider of 1, 2, 3, 1, 2, 4, and 8. So you enable it. You set you set a HFU. What is that? This is input to the HFOC circuit, and then enable it, and then you set an output, and then you set an output is int oscillator, which is a wire, and then you enable it as a 1, and then you put it as a 1 to just, yeah, cool. That's fine. And then in our specific case here, we have a divider basically. I'm so glad I opened this page. So here we go. You see, here we go. Here we go. Here we go. So in here, oh my word. How did I know to open this page? I would have struggled so much. Cool. And this is in where? This is in 7.4, hard micro primitives. Okay, cool. So this is fine. And then I want to see the ultra plus ones because I'm on UP. Yes, UP, ultra plus 5K. We can actually Google this, I2C UP 5K. What does that mean? I have another 10 minutes or 5 minutes between as I do this, and then we are going to go away and go from, so ultra plus, I2C ultra, I2C ultra plus, UP 5K. and I2C Ultra Plus with 5K lookup tables. That's where it goes. That's what it says. With 5K lookup tables. The I2C Ultra Plus with 5K lookup tables. So that's the UP5K. Okay, cool. So let's look at this technology library document, and then we're sort of going to be okay from there. I think so. I really think so. This is amazing. So what I want to look at is the Ultra Plus hard macros, I2C Plus, Ultra Plus hard macros. And then what I want to look at is SBI2C, SBI2C. What? IOD. It's here. Why is it? Yeah, oh, it's inside. So let's look at that. The ID is the open drain IO primitive, and when the tri-state output is enabled, the IO pulls down the package pin 0 to 0, and basically means it doesn't use any power. The following figure and Verilog template illustrate the complete user accessible logic diagram. We found a template. I'm so lucky. What? At the end of the thing, we find a template that describes to us how to do this. After reading this whole document, man, life is good sometimes. So cool. Cool. So this is all the pins that we need. But do I need to use these pins, or can I go straight into the SBI2C pin? Because look here, I can just, I can control this, and I can set them, and it goes through. It goes through. So I never set a clock divider here. I guess you can't pass it in, but you don't have to. Here you go. HVS, Verilog instance. So there is somewhere a Verilog instantiation here. Okay, cool. So SBID, and then what is this now? So SBID, package pin, largest hold, clock enable, input, dot. But what if I go here and look at this? Two I2C hard primitives located at upper left and upper right corner of the chip. That's fine. I don't know which one it is. So we're going to end up using where's the pinout? There should be a pinout somewhere. What I don't know is where this pinout is. So see this is there's going to be I2C somewhere here. Oh, it's not even labeled. Oh my what? Left I2C. So it's not even labeled. So we don't even know which pins it goes to. Before we even get to all of this, we need to find out which pins these goes to. Oh my word. Oh my word. This is fine. This is okay. This is fine. We will find out how it is connected. So, but this does not give us a Verilog instantiation of this, does it? No, it does not. No, it does not. It doesn't give us a Verilog instantiation. Even for the SPI, we do not get a Verilog instantiation. Device configuration frameworks. These are boots. That's cool. So let's actually go back here, and we know this one. We know this one. We can see it here. That's fine. We know there's a low frequency time. That's fine. We know there's an sRGBA, which we are using already. This is the one we're using down here to control the PWMs and such. So I think the task and let A IP. Oh wow, I've not used that one. Oh, LED drivers. I'm not gonna look at that one. So what I want to do is actually look at this one. And how many pages is this? Perhaps we can look at this. We can just read through this, and then once we've read through this, we're gonna stop, and this is going to be the end of today's thing, because I cannot go more than 11:15. I'm basically over time now. Let's read through here, and then we'll stop now. So the SBIO-OD, this is the open drain IO primitive. When the tri-state output is enabled, the IO pulls down the package pin signal to 0. The following figure and Verilog template illustrate the complete user accessible logic diagram and its Verilog instantiation. So there's an input when the tri-state output is enabled. Tri-state output is enabled. Somewhere we enable the tri-state output. Somewhere we enable the tri-state output. Package pin, latch input, so port signals. Package pin, latch input signals, clock enable, input clock, output enable, data out, data to package pin, data to package pin, data from package pin, data from package pin. So how do I enable? Output enable, that's fine. D out, package pin is in there, D in, latch input value. How do I enable the tri-state? When the tri-state output is enabled. When the tri-state output enabled. So this is it. This is it. When this is enabled, it goes into the IO pulls down the package pin signal to 0. The IO pulls down the package pin 0. Package pin to 0. This one is pulled to 0. Okay, cool. So package pin, bidirectional pin, IO, latch input value, input, latches holders the input data, clock enable, enables the clock signal, input clock, clock for the input registers, output clock, clock for the output registers, output enable tri-state output, active high. So this one, yeah, this is on. And then data to package pin, and then data out, data to package pin, D in, data from package in, data D in for package pin. Okay, cool. Default signal values. The iScript2 software assigns the logic O value to the all unconnected input ports except clock enable. Note that explicitly enabling logic 1 value to the clock enable results in a non-optimal implementation, since extra lookup tables is used to generate the logic 1. If your intention is to keep the input and output registers always enabled, it is recommended to port clock enabled to be left unconnected. Okay, cool. Parameter values. So pin type, binary, negative trigger, binary, neg trigger, that's it. Input and output function tables. Refer to SBIO input, SB function table for the pin input output tables here. Where is this table? Refer SBIO input and output pin function tables for the pin type settings. Some of the output configurations are not applicable to SBIOD. So another thing I want to come back to is my mentor's code and see if actually SBIOD is used. Okay, so I want to go in here. I'd like to go in here and go like SB underscore HFOC RGBA SFC LB SB RGB SB. Am I in the opinion that he actually just made his own I2C? Did he just make his own I2C? Here's the SBI lib. I see. So in some way it did, but it's fine. It's fine. This is okay. This is completely okay. So SB, the only thing it's using is the low frequency and high frequency oscillators. And if I go I2C, in, out, in, out, 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 out. Now we're gonna figure this out. Okay, cool. Look, I'm going over, and if I go over now, then I'll miss the next thing, and then I'll miss the next thing, and I'll miss the next thing. So thank you so much for those who showed up. Thank you so much for attending. That was amazing. So the task now is to understand what is happening in this technology library, and then we can now use we can now use SBI2C from in here. And I'm going to go ask some questions in the I'll show you in the Discord channel. So you can come here and you can go Upduino documentation, and you should be able to, if you go to support or something, let's see, where can you buy the Upduino? Tiny Vision Upduino. Tiny Vision Upduino. Here you go. And I think there should be a support server somewhere here. Yeah, read the docs, GitHub, PMOD ecosystem. There should be a way to contact us. If you go to contact us, is there something? Is there something you can chat with someone or someone? In any case, there is a Tiny Vision about us, maybe. Yeah, this is all of that, but there should be a Discord somewhere where you can talk to us. There should be a Discord. Anyways, so I can go like this: Tiny Clue NX33. Here, I'll show you on the stream so that Discord chat. You can go to this link, and you can get support from. You can get support including for the Upduino server. Okay, cool. Thank you all so much. I'm going to have to stop there. We've gone 7 minutes over. I can't keep going because I'll miss the next thing. That was really lovely. We have sort of learned what we want to do, and we know where the information is. The one thing that we need to do is to learn how to combine it all and make it one thing. Thank you so much for showing up today. That was an amazing stream. Does anyone have any questions? Does anyone have any questions so far about what we've done, where we are, and everything? And I'll actually, the final thing I want to do is, let's commit this. Git status, git init, git branch dash m main, git branch ls and vim here, and then what I want to do is make a .git ignore, and then I want to take builder build, and then yeah, and then there's that, and then git status, git add, git commit -n, initial building project for RT account, git push. Actually, I need to make a repository. GitHub, which let's make one really quickly so that people can get to it. Repositories, and then we can make a new one, anyone, we can say RTL com. RTL Digicam. An attempt to build an RTL camera Digicam during AOC 25. Yeah, it's definitely not 1925, yeah. And this should not be private, it should be public so that people can use it. And then let's do that, and let's add this. Git push -u origin name. Okay, cool. So I'm pushing that up, and it should be up, and it should be public. There we go. And I will add this into the description of the video. It's code we're working on. There we go. Code we are working on. Okay, cool. And then I will relabel this part 1. Okay, and then that's cool. Amazing. Part 2 in short order, probably tomorrow. Thank you all so much for coming today. Unless anyone has any questions, I'm gonna bid you goodbye, and remember, always be daring, do stuff, make stuff, break stuff. Cheers so much. We'll meet. Yeah, that's it. End stream.